Okay. We'll get some things passed out. We'll start here, but let's just do one stack. I'll do one over here. Please make sure it goes all the way around, and then go to the other side and back down. Okay, keep it going around. At the end of class, or sometimes, please, if you'd bring down extras. Okay, you don't have to do them immediately, but please make sure those get brought down for me, if you would. You can go across. I would typically go this way and then come back down. That way, the extras will end up down here. I would go this way, just pass it behind you, up, and then back down over here. Okay, it takes a good amount of time to pass things out with such a large class. Occasionally I will send you things for you to print on your own, okay? And to have them here in class. I'll give you enough lead time to get that done, okay? I'll send you a variety of emails throughout the semester. Make sure you're receiving them and reading them, etc. Everybody have a syllabus? Where's the syllabus stack at? Everybody got one? Okay, you should have the syllabus. Everything's here. First page, all the standard information, course requirements, textbook. Textbook of record is the book by Klein. Everything was mentioned in the email. Klein 3rd edition, I believe it's paperback in the bookstore. 2nd edition used to be hardback. Okay. But as I've mentioned, you can use any textbook you like. Okay, most of them are all the same information. And basically, we proceed by topics, not by a textbook. Okay? Regardless of what textbook you have, you need to have the solutions manual that goes with it, because you need to be working problems from your textbook. Okay? And the solutions manual will give you the answers. All right? If you do not have how to read a textbook, work problems, and use a solutions manual, you're going to have difficulty. You need to do that. All right? Also, a laboratory techniques book. Okay, there's a lab component. Laboratory textbook of record is the book by Morag. Okay, but you can use any other textbook you want for that purpose. We used to use one by Zubrick. This will cost you $100 in the bookstore. You used to get Zubrick online for like a penny plus shipping. Okay. Need to be prepared for lab. These books cover the so-called laboratory techniques. Right. Other things pretty straightforward. Workbook. I unfortunately left my workbook upstairs. I produced a workbook. We discussed this at the meet and greet. It contains both workbook. Anybody have workbook that I could maybe use and show? Thank you. Thank you. Thank you very much. Workbook here. Upstairs in the main office. Can only be purchased upstairs, $15 cash only. The first half is the workbook. The second half is the lab manual. I just call this the workbook. All right. Now this gives you extra problems to work. These problems laid out by me, and thus will be more in line with what you'll see on the test, because the test is also made out by me. All right. That does not mean you cannot be working problems in your textbook and using your textbook. These problems tend to be more intermediate and advanced. Okay. The more introductory problems in your textbook. If you do not use your textbook to get the foundation, you're going to have difficulties. All right. Lab manual portion. There's a number of guidelines. Such as overview of lab safety guidelines, requirements for lab reports, notebooks, etc. Instructions for checking in to lab, which we will do this week, either Thursday or Friday, right? Okay, 2:30 upstairs. For check-in, instructions are there. You need to have the lab manual, so you will have the instructions, and well in advance. Some guidelines to using certain instruments, other helpful information, and then the labs we will be doing. I used to call everything here used to be a handout. Okay, I used to give lots more handouts than this. Okay, now a lot of this is in the workbook. Okay, the labs used to be handouts, so I still refer to these as the handout. I'll say, okay, let's go to the handout, the hydration or null warning handout. Well, it's right there. All right. So, need to have that. Other things there, video recording, course overview, important dates for the class. In the back, test schedule, grading, etc., etc. Some general comments. A couple pages over is our daily outline. Okay. Where are we at? Today, August 14th. Chapter 1 through 2. Now these chapters do go with Klein. But again, Lewis structures. Any textbook you use is going to have a chapter or a section on Lewis structures. That's where you want to be, and you want to be reading and working problems there. I guarantee you the problems are going to be almost identical to problems in any other textbook. Same type of things. There's enough variety that it's all the same. Okay? I imagine most of you are using Klein, but I know a couple of you are not. I don't want you to, the requirement is not to buy a $300 textbook. Okay? If you got a $5 free textbook, let's make that work. All right? You got to be comfortable enough in being able to do that. If you want to pay $300, then you can do that. You guys will see as we go along. Okay, schedule for the lab is on the far right. What are we doing this week? Lab check-in, already mentioned that. Then we're going to go downstairs and have IR and DUS functional group lecture. Okay, check-in instructions and lab manual. All right, this is the labs we're doing each week, right here. On the last page is structures of some common drugs. My background is in medicinal chemistry, drug development, organic chemistry related to that. I will use organic drugs to illustrate organic chemistry principles. Okay, I use that drugs a good bit. Did I say that? Drugs a good bit? Yes, I did. Many of you have taken some of these. Tylenol, yeah? Okay. Good looking compounds there. On the very back, there's ibuprofen and some questions about the ibuprofen. These types of questions up here we should be able to answer as we move through the course, and hopefully we can get done through the course. There's a couple of questions below. More advanced questions, these are types of things you may see in upper level courses as you move ahead, like in pharmacology, or if you take maybe a class on the medicinal chemistry of anti-cancer drugs. Okay? This is a prereq to other courses. Biochemistry. Okay? Prereq to Organic 2, yeah? This is a 2-semester sequence typically. And by the way, the final exam in Organic 2 covers material for both Organic 1 and 2. So right here today, you're beginning to prepare for the final exam in Organic 2. And of course, the final exam here in Organic 1. The final exam in Organic 2 is the ACS Comprehensive Multiple Choice Exam. There is an exam guide for that. You can get it now, might as well. One of my goals for you is to score very well on that, such as 90 percentile. I always have a good number of students who do that. On this Friday morning, I'm going to present a certificate to my previous students from the spring who scored 90 percentile on that ACS exam in Organic 2. We'll do that at 7:55 on Friday, because a couple of them then have to get to an 8 o'clock class. All right? Hopefully next fall, I can be presenting you with a certificate. New Organic 1 next fall. Okay? So some goals to be working towards, yeah? The final exam in Organic 1, mine is I make it out myself. Okay, it's not standardized. In Organic 2, I do use the ACS exam. But of course, all this is written down somewhere, because anything I tell you is going to be written down. Okay? I'm big on reading the instructions, following instructions, because if it's written down, it should be very clear. I don't have to repeat it over and over. You don't have to say, what did he say? I missed that? No, you didn't miss it. Everything is written down. Okay? Thus, I expect you to read guidelines. Okay? Among other things, if you don't read guidelines, there'll end up being issues along the way. I got a little friend here that I use on things to indicate, and it says, read guidelines, okay? And if you get that, it'll probably also be a deduction of points and stuff like that. In the end, guys, got to learn how to read. I don't know if you guys are expected to read information and guidelines in other courses. This is Organic 1. It could also be called how to follow directions, how to read instructions. Okay? Hopefully you'll find that will make everything simpler, easier, okay? You don't have to worry what's the expectations. All right? So I'm kind of big on that. All right? So if you can do it, great. If not, you need to start working on it. And that's a large part of my expectation. There's more than just learning content here. Content is only half the course. The other course is intangible soft skills, okay? Working hard. You can look at writing letters of recommendation where I talk about that, the number of things that you're evaluated on. Okay, only a portion of the letter evaluation is your course performance. It's a lot of other things, okay? For example, I mentioned you need to be ready to go at 7:55. Okay, walking in at 8 o'clock is just not good. All right? It's a little bit disruptive to anybody else who's here ready, trying to get going. You're also not doing yourself any good, because walking in late, how can you be prepared to go? All right? So make sure you leave early enough to get here. Shoot for 7:50. I'm going to get here early, and I a lot of times answer questions before class. Okay? Don't be walking in. That's one of many things. All right? Some of this is discussed in the syllabus. All right. It'll take us a couple of days to sort of get everything sort of launched. Okay. I don't want to go on and on today. I kind of want to discuss things as it's necessary. Any questions? Any questions? Everybody get every handout? Okay, your first assignment is to make sure you have read the syllabus and to ask any questions on Friday morning. I'll say any questions. All right? Of course, you can ask questions any other time as well. All right? You know what's in the syllabus. All right? I say I write things down. If anything is ever not clear after you've read it, say, Dr. Stevens, I read right here, but could you explain this? I said, sure. What I don't like is when you ask for something, I'm like, but that was said right here. You obviously did not read it. All right? Don't do that. Okay, blank slate, right? You guys are a blank slate. Mostly. You know what organic chemistry is? Carbon? Yeah. Okay, we'll focus on carbon. There's a lot more to it. I said before, but you guys are going to be amazed at how much you learn along the way, particularly come April, Organic 2. Okay, you can think back right now of how sort of like, what is this? What am I getting myself into? You're going to know so much more. All right, and your world will be changed, and you'll be able to go forward and use organic chemistry in many different classes. And in many walks of life, if you're going to do some type of scientific career, all right, huge application. All right. The other thing is you got to know why you're here. It's got to be more than I got to take organic chemistry. You got to realize the importance of organic chemistry and what it's going to do for you. All right. If you want to be part of the scientific community moving forward, you got to know some organic chemistry. All right. Particularly as you continue on through your academic career, because organic chemistry, okay, I don't want to go on and on. Everybody get other handouts. What do we have? We had a white one. Functional groups we'll look at in lab this week, lab lecture. We got syllabus, that was the white one. I get the extras at some point. Green, outlines. I typically give what I call an outline. And this would be where we would start, typically on colored paper. Okay? Put this one on green because green means go. All right? Yellow is the DQ page. These are some extra questions. There's questions all over the place. Okay? You got to be working problems, so that's how you assess your learning. All right. And you got to be sort of, well, you got to work problems, and you want to make as many mistakes as you can, okay, each day. Because if you make mistakes, that's how you learn. If you're not making mistakes, you got to be a little concerned. Right? So a little bit, sometimes faculty will say, you know, you got to make mistakes, assess your learning, because you don't want to make the mistakes on test day. All right? Get them all made before test day. Let's try to get going here. Well, the DQ are, as it explains there, are questions that sort of go along with the lecture. These are also questions where you all know that they may be coming. We might talk about these. 100 other questions you don't know that we might talk about them. But these are ones we may talk about in class, so be particularly prepared for these. Okay? That's sort of the idea there. Did we cover every handout? I think what do we have, 4? Is that right? Okay. Any questions at this point? Y'all want to review atomic structure? We need to review atomic structure. How are we doing with atomic structure from Gen Chem? Good to go? Gen Chem is a prereq to this course, Gen Chem 1 and 2. Everybody got your Gen Chem book? I'd recommend you keep it handy for reviewing. Yep. Okay. Want to skip over atomic structure? Want to take a look at it?
Let's get at it.
What?
Let's get at it.
Want to take a look at it?
Yes.
Okay. What we got? Protons, neutrons, electrons. How many? Well, we mentioned carbon. How about carbon? Carbon 12. What's the atomic number of carbon? 6. Is it 6? Periodic table. Everybody know periodic table, periodic trends? Yeah, there's a periodic table on the back of the workbook. Okay? Yeah? Let's see. Number of protons. 6. Number of neutrons for this guy here. 6. Number of electrons, assuming it's a neutral carbon atom. 6, yes, 666. Okay, that's carbon. That's carbon 12, so-called. Okay, but we can have. What about this? Isotope of carbon. Yes. Do we really need to put that 6? No, every carbon is 6. Okay. What's that number called? Yeah, mass number, and these are isotopes, yeah? They vary in terms of number of neutrons. So this here, number of protons is what? 6, and neutrons? 7. And electrons? Yeah, just vary in terms of that. What else do we have? How about carbon 14? We got 6. Okay. These are natural here. Well, they're all natural. Yeah, they all are. What's the percentage of carbon 12 in your body? 99. That's 99% approximately. And carbon 13? 1. About 1%. Carbon 14? It's a trace amount. Okay, I rounded these off. Trace amount. What's unique about carbon 14? It's radioactive. Yeah, the other two are not. Since it's radioactive, it can be used for carbon dating. Okay. Y'all familiar with dating? Yeah. Yeah. Are there any other isotopes of carbon? Yeah. Are they?
Yes.
What are they? Whichever ones you want to make. Okay, like what one? Which one? What? Carbon 11, yes. These are natural carbon isotopes. There are artificial isotopes that can be made. Yes, there's many of them. If you look on Wikipedia, carbon isotopes, it'll show so many of them. Carbon 11 is one of them. What is carbon 11 used for? A major use of carbon 11 is for PET imaging. This shows a PET image of a brain scanning to look for Alzheimer's disease. On the right is good brain. Over here, lots of indication of Alzheimer's disease. This is a PET scan, positron emission topography. Positron, what's a positron? Well, this molecule is used, it goes to the brain and localizes there because it binds to certain things, particularly Alzheimer's, beta-amyloid plaque, stuff like that. And where it localizes can be then scanned. This compound has a carbon-11. Carbon-11 is radioactive, it emits a positron, and that's what gives the image. Okay, lots of ingenuity here and innovation. Organic chemistry, though, there's a nice organic molecule. Carbon-11 has to be man-made, but then the molecule is man-made. It's a synthetic compound. Okay, how do you make organic compounds? Well, we'll certainly be talking about that a lot. But there is an application of carbon-11. The black and white is in the second page. Okay, hydrogen. Does hydrogen have any isotopes? Hydrogen is very important in organic chemistry. Lots of carbon-hydrogen bonds to be found. Look on the back. Discusses hydrogen isotopes. Deuterium is a non-radioactive isotope of hydrogen in which it is H2. Regular hydrogen is H1, no neutrons, just a proton. And that's why we call H plus just proton. That's all it is. If it has no electron, it's positive. H plus is just a proton. That's why we call it that. Deuterium has a neutron, and so it has a proton and a neutron. That equals 2. That's why the number is 2. But we don't call it H2. The hydrogen isotopes have their own names. We call it deuterium. Maybe the D came from di, like di, mono, di, tri. I don't know. 2, deuterium. We will see a deuterium a good bit. Deuterium is actually more and more incorporated into drugs. Some example here. Hopefully there's enough to explain that. Written here, largely the effect is because the CD bond is stronger than the CH bond. That makes the bond more stable, more difficult to metabolize, and thus the drug may last longer in the body. You can read about that. We'll talk about the CD bond strength near the end of the course. But you'll see deuterium along the way. You also have H3, which is called tritium, tri. Okay, tritium is radioactive. Tritium used to be used at the Savannah River site. I don't know if they still deal with it there or not. You don't see tritium as much in textbooks and problems, but deuterium is seen a good bit because it gives variation that's needed for certain reasons, particularly when we get to stereochemistry. Okay, so you need to be familiar with isotopes. Electron configuration of carbon. Okay. What do we have here? How many electrons do we have for the carbon? 6. I haven't done electron configuration in a long time. What do we start with? 1s? Yeah. And then what? 2s. 2s. And then? Okay, and we got, boom, 3 of these. And we know a lot about these atomic orbitals. Degenerate shapes, bulleted shapes. How many electrons? 1, 2. What we got? We got some rules. Pauli principle. Hund's rule. Pauli exclusion principle. Hund's rule. Those 3 are the big ones for doing this. Yeah, 1, 2, 3, 4, 5, and 6. Is that right? Does that look like ground state? What do we call this shell here? Second shell, but it's also valence electrons. Okay, and how many valence electrons carbon have? 4. There they are. That's where we do bonding. Carbon wants to achieve what to be happier? Octet. It wants to become like neon. It wants 4 electrons. It's going to get those 4 electrons from bonding. Okay. By the way, why is carbon so magical? Why don't we have a class on just nitrogen chemistry?
Carbon is trivalent, forms 4 metals.
Yeah, nitrogen's trivalent, forms 3. So, the The reason is carbon is such a friendly bonder. It likes to bond to many things. Okay? It bonds to nitrogen, oxygen, halogens, silicon, phosphorus, sulfur. Very friendly bonder. Okay? Makes particularly strong bonds. Because of that, you have all types of carbon types of compounds. Silicon, just below carbon. You see very few silicon-silicon bonds. Carbon likes to bond to itself over and over and over, so you get these long carbon chains and rings. Not silicon. It's just something about carbon. Okay? Nature gave us carbon to do all this with, and it doesn't.
Do you know why it's like so friendly?
I can give you some spill on it, but I don't have a short answer. You know, strong bonds, but that really, you're asking why is it strong bond, right? I mean, that really didn't get you got to look deep into it. Okay. Okay, valence electrons. What else would we do here? Ground state. That's ground state, but carbon bonds in a hybridized state. What is hybridization? Well, first off, it's just a fancy word for mixing, blending. That's what hybridization is. And what are we blending? We're blending orbitals. How are we doing it? It's all math, really. It's math and it's theory. We look at enough to make it work. Why do we do this? Because it fits real life. Okay? Carbon makes 4 identical bonds on methane. We'll talk about this. How do you make 4 identical bonds with this setup? You can't. That looks like a lone pair. Carbon doesn't typically have a lone pair. So this doesn't fit sort of reality. So we have to, the theory of hybridization was developed. Okay? And nobody else has come up with a better theory yet. If you do, let us know. Let's publish a paper and maybe we can change organic chemistry. But right now it's sort of this is the theory. We're going to learn about it. Hybridization. Valence electrons, types of orbitals. What's an S look like? Spherical, like a volleyball, and the nucleus is in the middle, yeah? Okay, that's supposed to be round. And electron density all here, you know what an orbital is? How about well, what's the difference between 1s and 2s?
Size.
Yeah, larger. Remember going up in shell. Okay, larger orbital. That's the main thing, main answer to me. What's a p orbital look like? Yeah, it's a dumbbell. There's actually a node here. There's no electron density at the nucleus. Okay, so we'll call them. But we'll mix those and we'll make hybrid orbitals. Okay, but you should have a foundation there to start with, and you're ready to go. Bonding. Okay. So we did carbon here, but you need to know how to do that with, you're going to have a periodic table. Tellurium. How many neutrons does tellurium-128 have? Okay. Questions like that. The same questions we ask here, but you need to be able to do it with others. And you found tellurium yet? Yeah, it's right below oxygen. Oxygen, sulfur, selenium, tellurium. Okay. Covalent bonding. Let's see, we can have a hydrogen. How many electrons? 1. That'd be just called a radical, something with a single electron, typically not happy. Hydrogen wants to be more like what? Helium. How many electrons does it need?
1.
It needs 1. Where's it going to get it from? Well, if we have another hydrogen that also needs 1, they can say, hey, why don't we team up and sort of share this electron, right? And this can come together, and now the 2 kind of sits there, and they're being shared. And this is the magical sharing there. And so we indicate the 2 electron covalent bond, shared bond, by just a dash, right? Okay, so when you see that, how do they share the 2 electrons? Oh, well, that book is this thick right here on the covalent bond. Okay? You got to have just a simple understanding of that, and you can go very deep, but we're not going to go that deep. All right? 2 electron covalent bond now shared. But the important thing, the magical thing is now this H nucleus gets to count both electrons as if it belongs to that. And so now we have sort of the shared count, and now we say this H has 2, but this H also has 2. It sounds like 4, but there's only 2 here. It's the sharing idea. But now each sort of has 2 electrons around it, it's a simplistic sort of argument there, and now each looks like helium. All right? And you may have talked a little bit more about that, but rather simplistic approach that we will not really go beyond. Again, you can buy the book. It's called The Nature of the Chemical Bond. I think it's by Pauli. You can get an old copy if you want to read more about that. Okay. So hydrogen makes how many bonds? It only needs to make 1 bond because it only needs 1 electron. Each bond you make gets you an electron. And we say hydrogen has a duet. Each H has 2, a duet. Let's look at carbon instead. And I think with these, we're going to do carbon-nitrogen. We're going to come across, so leave some room on your paper. We're going across and then down. Carbon. How many valence electrons? H has 1 valence electron. How many for carbon? 4. Okay, let's put these around carbon. 1, 2, 3, 4. Got 4, not 1. How many does it want to have around it? 8, and that's called an octet. H was duet because there's nothing but H and helium on the first row. The carbon is on the second row. And the second shell can contain how many? 8. That's why we're dealing with 8 here. Okay, how many bonds does carbon need to make? Thus 4. And we can bring in maybe a hydrogen. And here I'm going to call the hydrogen electron an X. So we can bring in an H. Remember it had 1 electron? So the H electron teams up with a carbon electron and we make a magical 2 electron covalent bond. But we do that 4 times. Now how many electrons around carbon? We get to count all the electrons. 2, 4, 6, 8. And we say carbon now has an octet and it has the noble gas configuration of neon. All right? And all that magic there. Well, we typically, we show this as a dash, right? You know that's what's going on with these dashes, yeah? And what's the formula of this? This is a compound, CH4, or this is called methane. This is our Lewis structure. Lewis structure, we show all covalent bonds. We also show lone pairs. Is there any lone pair here? No. This is standard bonding for carbon, which is what? 4 bonds, 0 lone pairs. LPs. Standard bonding for carbon. Let's do standard bonding for nitrogen. How many valence electrons? 5. 1, 2, 3, 4, 5. How many does it want? 8. How many bonds do we need to make? 3. Each bond gets you an electron in terms of your count. We bring in an H. By the way, we can bring in a carbon. We could bring in a variety of things. I'm just using H. Bring in another H and it's 1 electron. Bring in another H and it's 1 electron. Do we need to bring in another? No, you can, but we're doing standard bonding and looking for octet. How many electrons now around the nitrogen? 2, 4, 6, 8. The nitrogen now has an octet. We can show this more with dash bonds. And what do we have here? We have a lone pair. This is standard bonding for nitrogen. which is what?
3 bonds, 1 lone pair.
3 bonds, 1 lone pair. It doesn't need another bond to H. How about oxygen? By the way, this is NH3. What is this? Ammonia? Yeah, NH3. When we show NH3, we typically don't always indicate the lone pairs there, but you got to know it's there. Oxygen, valence electrons. Why am I going around 4 times and then pairing up? Why don't I just put 6 separate ones around?
Fill one.
Because really what I'm doing is I'm filling those orbitals. And how many valence orbitals do we have? 4. I mean, you got to know all that over there. The answer is 4. Yeah, it's because really we're filling orbitals. Okay. We come in here and team up here, make it bring in an H and just 1 electron. Does that oxygen look good now? It's got an octet. What do we have? Dihydrogen oxide? Yeah? Gotta be careful with that. H2O, what do we got here? Standard bonding for oxygen. 2 bonds, 2 lone pairs. Okay, let's do fluorine next. Group 7, what's the name of group 7? Halogens. Bring in 1. All we need to do is make 1 bond to an H or a carbon or anything else. And we have HF, but how many lone pairs on the F? 3. Does F have an octet? Yes, 2, 4, 6, 8. HF is it's an acid, hydrohalic acid. Standard bonding for their halogens. 1 bond, 3 lone pairs. Okay, this is standard bonding. I'm not going to waste ink there because it says that somewhere. For example, our typical covalent bonding. All right, this is where it comes from. Basically looking for an octet. If you see an atom that is not standard bonded, it's probably going to have a charge. Okay? We'll see non-standard atoms a lot. They're probably going to have a charge. I would almost say always have a charge, but there's an exception or 2. There's an exception or 2 for everything we do. All right? And we will talk about charge, Lewis structure. Important considerations there. Okay? Structures with single bonds. All right? We're going to have to start putting structures together. How about CH4O? I mean, I might have could have asked you to do a structure there, and you probably wouldn't have been able to do it. Okay? Now, organic chemistry builds. Okay? All right? Believe it or not, my presentation to you builds strategically. What do you need to get out of this information right here? So when you look at information I present, we talk about, what do I need to know here? And then as I move ahead, do I ever need to refer back to this and make sure that I incorporate this into my sort of thinking? Yes. Otherwise, why did I show it to you? I don't want to waste your time. Okay? So everything's important. Hopefully you'll see a sort of strategic process. Now let's move to putting structures together. Okay? Put a structure together here. A Lewis structure which shows all covalent bonds and lone pairs. And charges if they're charged. Charge is part of a correct structure. By the way, Gilbert Lewis wrote that big book on the nature of the covalent bond. Okay, how would we do this? How many bonds does H make? One. It's always on the periphery then. It can't be in the middle. All right? But C and O can make more than one. I would bond your heavy atoms first. That means not hydrogen. Heavy atoms, C to O. Next, I would fill the, well, this is where I would start with. We got to put all valence electrons up here. That's what, okay. How many valence electrons are we dealing with? Total. How many does carbon have? 4. 4 H's is 4. Oxygen? 6. What's that? When we get down, we need to have 14 valence electrons shown. Yeah? So let's make sure we... Okay. H's. I would typically fill the valence of carbon first with H's. Right? H. How many H's can we put on carbon? 3. Yeah. Where's the other H go?
On oxygen.
Right?
2 lone
Are we done?
pairs. 2 lone pairs.
2, 4, 6, 8, 10. I've only got 10 electrons. Oxygen has no octet. What can we do?
2 lone pairs.
Here you go. What's standard bonding for carbon? 4 bonds, no lone pairs. Standard bonding for oxygen?
2 bonds, 2 lone pairs.
2 bonds, 2 lone pairs. See how things fall into place? Do we have 14 valence electrons here?
Yes.
Oxygen and carbon both have octets? Yes. Each H has a duet by making 1 bond? Yes. There you go. There's your good structure. All right. How about C2H6O? Okay. Sort of in the middle here are sort of some clearly sort of like questions or what we're going to do. Like D, it looks like trying to do a structure of HCN and it's indicating something about a triple bond. All right. Now this is essentially homework if we end at a certain point. What I expect you to do is sort of do these things. It's not going to say, hey, homework here, please do this. No. You need to see what we're going to be doing. You need to be, okay, let me try this before class so when I get to class I can be more prepared to ask questions or to know what I need to be looking out for. Okay? So you need to be looking ahead in your handout. Some cases it may actually say homework, but a lot of times not. You just need to know, expect what we're going to be doing. 2 constitutional isomers. I'd recommend looking up what that is. See a term like that. Okay. Again, I'm not going to give you something just to. It's not like the type. Constitutional isomers, you need to know what they are. All right, and that'll be our first look at it. What I'm getting at is preparing for class through using my outline or the other handouts. Okay. Shall we do a C2860 real quick? And any questions? A lot of times I'm erasing. That's a great time to shout out a question. How many valence electrons? C2H6. Each carbon is 4. What's that? 8. 6 and 6 is 12. 20. 20 valence electrons. Let's see. Carbon. Let's bond their heavy atoms. Carbon. Oxygen. We can make carbon happy with these H's we got. How many H's we got? 6. Carbon happy. Carbon happy. Where's the sixth one gonna go?
On the oxygen.
Yeah. How many valence electrons we got on the board? It's probably 16. We've got to put 20. 4 more. That sounds like 2 lone pairs. Any place for 2 lone pairs?
On the oxygen.
Yeah, standard bonding for oxygen. There we go. 20 valence electrons. Everything has an octet. H has to do it. Okay. Is that the only structure we can put together here?
No, you do see.
Put the other one together. I think there's another one, and it's called a constitutional isomer. Okay? How are we doing on time? Is that it? Looks like it's it. 7:55, we'll present certificates to the previous students. And we'll see what type of questions you have about the syllabus. But some of you will be checking into lab tomorrow, yeah? So we'll see some of you